We have an integral that we looked at earlier in the course to be able to evaluate by integration by parts. And this time what we're going to do is we're going to use a table. All right, so this is actually a pretty easy one to use a table on, although it's extremely difficult for us to be able to integrate by parts because it uses the iterated integral method. So we're going to go back and let's take a look at our table of integrals and see if we can find something in the form e to the 2x or e to the ax cos bx or something like that. All right, so go back here, and it's probably going to be somewhere in our exponential or trigonometric. So certainly not here, like a plus bu. That doesn't make a lot of sense. So we have our trigonometric forms. And notice in all the trig stuff, it doesn't have like an e to the x. All right, so we're going to go down to inverse trig. That doesn't make any sense for us. But notice we finally get right here. Looks like 99. Okay, we have e to the au cos bu du. Okay, that's precisely what we want. Okay, so in this case, we're going to use entry 99. Okay, and we're going to have where a is equal to 2 and b is equal to 3. And what we're going to do is we're just going to plug it right in here. Okay, so I'm just going to pull this off to the side and I'm going to copy it over. So give me 1 sec. All right, so pull this off to the side, and our integral is going to be equal to e to the ax. So it's going to be e to the 2x. And that's going to be divided by a squared plus b squared. So it's going to be 2 squared plus 3 squared. All right, certainly you could write that in as 13 if you wanted to. All right, and then we have a cos bu. So that's 2 cos 3x. And then plus b sine of bu. Okay, and then there's a constant of integration. All right. If we wanted to, we could certainly distribute that through. All right. And so another answer we could get is 2e to the 2x cos 3x divided by 13 plus 3e to the 2x sine 3x divided by 13 plus c. All right. So now what we could do is we can verify this, or at least see if we get anywhere close by using Wolfram Alpha. Okay, so I'm going to go back and I'm just going to use Wolfram Alpha here, and we're going to integrate exp of 2x times cos of 3x with respect to x. All right, and I'm going to go ahead and run that. And remember, there's a 13 in the denominator. So if we've done it right, okay, so here it is. And I want you to notice that they factored out the e to the 2x and they factored out the 13. So the version that Wolfram Alpha has actually looks pretty close to this version right here. They have 2 cos 3x, 3 sine 2x. And if you go back here, they have their 3 sine 3x, 2 cos 3x. All right, so pretty close, okay? And they have a plus constant at the end. So pretty cool that we can use this both ways. And remember earlier in the course, this was a pretty lengthy problem. Okay? Now another example, okay? So we have this 5 plus tan square under a square root and then cos square x. All right, so this is a tough one, all right? Because we could do this by hand if we elected to, all right? But it would be really tough for us to do this, all right? What we're going to have to do before we do anything is we're going to have to use a u substitution, all right? And of course, whenever we do a u substitution, the first thing we might try is u equals 5 plus tan square x. And du, the derivative of tan square, is going to be a chain rule. So it's going to be 2 tan x, and then multiplied by the derivative of tangent, which is going to be secant square x. Or another way to write this would be 2 tan x divided by cos square x, right? And that gives us the cos square, it gives us the dx, but there's this 2 tan that's floating around, and that's no good, all right? So what I'm going to do instead is I can't just do a straight u substitution with this one, okay? At least to get to the direct answer. So instead, what I'm going to do is I'm going to let u be equal to the tangent of x only. And then the du is going to be sec square x dx, which is the same thing as dx over cos square x. And that's something that we can at least try to use, okay? So when we substitute, now we get the integral of the square root of 5 plus u square du. And from here, we're going to try to use the table. All right, so let's go back to our table and see what happens. All right, now we're looking for something of the form, and we're going to hope to get this, like the square root of a square plus u square or something like that. We're looking for that form. So if we go back to our table, let's see if there's anything in there. All right, so I'm going to scroll up. The transcendental functions are lower, and by transcendental, I mean like sine, cosine, inverse cosine, hyperbolic tangent, logarithms, that sort of stuff. The algebraic functions are up a little bit higher. All right, so this one's close. We have u square plus a square. All right, but that's not what we want. We have a square minus u square. All right, close, but no cigar. And finally, if we go a little bit higher, we get a square plus u square. All right, so that's perfect. In fact, 21 is precisely what we're going to use. All right, now in this example, we're going to use entry 21, where u is equal to u, all right? But also a is going to be the square root of 5. Okay, so it's not a nice number, but if you get bit and it hurts you, just let me know. I don't think it will bite you too badly. All right, we're just going to substitute immediately in right here. Okay, at least for the first part. Okay, so that's going to be u over 2, square root of a square plus u square. So that's going to be 5 plus u square, plus a square over 2. So that's going to be 5 halves. Natural log of u plus the square root of a square plus u square. All right, and then there's a plus a c at the end. All right. Now, of course, we're not going to stay with u. We're going to go back and put it in terms of x because u is the tangent of x. All right, so this is going to be tan x over 2 square root 5 plus tan square x plus 5 halves natural log of tan x plus the square root of 5 plus tan square x plus c. All right, so let me see if I can squeeze that in there again. Let me rewrite that a little bit better. So it bothers me probably more than it bothers you all, but regardless. All right, so square root of 5 plus tan square x. All right, so that is our answer. And of course, to evaluate this by hand, the integral, even after the substitution, we would certainly need a trig sum where u was going to be equal to square root 5 tan of theta. All right, so that's how we would have to do that one by hand. And that would get pretty ugly pretty quickly. All right, now let's go ahead and see what Wolfram Alpha is going to give us. All right, so let me go back. And now remember, our original integral was going to be the square root. So square root of 5 plus tan of x squared. And let me make sure I'm using enough parentheses here, or not too many. All right, so that's the square root of 5 plus tan x squared divided by the cosine square. All right, and it looks like I'm missing a parenthesis somewhere. All right, so let me just go ahead and throw that in. Let's see if that works. All right. This x square. I'm just trying to make sure that I didn't make any errors. I think I forgot to close off the square root here. And I might have added this extra one. right here. All right, let's try that. That's another frustrating component of this. All right, so that's my input and this is my output. Good luck to any of you that would like to try to verify that what we got here is equivalent to this. Okay, so we have an inverse hyperbolic sine, I'm sorry, an inverse hyperbolic sinh function. Okay, so yeah, you can see that this is a pretty rigorous sort of manipulative. All right, in fact, it even wrote the square root of cos square instead of just cosine. Okay, that's just the way that the computer algebra systems work. Okay, they have their own algorithms as to how to evaluate. So, not saying that this is incorrect, but it's a pretty difficult and rigorous sort of process. Okay, so now we can see the benefit of using the tables over the computer algebra systems sometimes. Okay, and there's certainly benefits to doing it by hand without using the tables as well. All right, so in the next couple videos, we're going to have a few more examples of being able to do our table or use our tables as well as our computer algebra systems. But we're going to step up the rigor with a little bit more of the algebra necessary to prep it for using the tables or the table of integral or the computer algebra system.